Now let's see the difference between the mirrors and the lenses. This is a convex mirror, this is a concave mirror, and this is a convex lens, and this is a concave lens. Okay, so these are mirrors and these are the lenses. Now let's see the difference between them. Now a mirror is opaque, it's not transparent. The rays of light cannot pass through this. Okay, the rays of light will be reflected. They cannot pass through this because it is opaque. Whereas lenses are transparent. The rays of light can surely pass through them and reach the other side. Okay, that's the first difference. This opaque. The mirrors are opaque, whereas the lenses are transparent. Now the next difference is the mirrors will reflect the ray of light. Okay, it will fall on the surface, the incident ray, and it will get reflected in both the convex as well as concave. They reflect the ray of light falling on them. Whereas here, as they can pass through them, they are not getting reflected, but they are getting refracted. And we know what is refraction, the bending of the ray of light when passes through one medium to the other. So here they refract. Mirrors reflect, whereas the lenses refract the ray of light. Now the third difference is the center of the reflecting surface of the mirror is called the pole. Okay, here you have the pole marked with capital P, and we know that a ray of light which passes through P, through the pole, is reflected in the same direction without any deviation. Same way for the lenses, it's not pole. The center of the refracting surface is called as optical center. It's marked as O. It's O, optical center. So a ray of light passing through O will come out without any refraction, without any deviation. It will pass straight through this. Now the next difference will be, this is your convex mirror, and it is also called converging mirror. Diverging mirror, because you can see the rays of light are getting diverged. Whereas if you, at the same time, if you see the convex lens, this is convex mirror, it's called diverging mirror. This is convex lens. The rays of light, after refraction, they meet. So it is converging. It's a converging lens. Convex mirror is diverging mirror, and convex lens is converging lens. They converge. And here, this is a concave mirror. The rays of light, after reflection, they meet at a point. That means they converge. So they are converging mirrors. Whereas if you go for the concave lens, the rays of light, after refraction, it emerges out. That is, they are diverging lenses. Now for the ray diagram for the mirror, which we have already done in the last class, we had the center of curvature, the principal focus, and the pole. So we started from here, 2 cm, C to F 2 cm, F to P 2 cm, and keeping the compass at C and CP as the radius, we draw this arc, and this is M and N. Okay, so you have C, F and P. But for the lenses, if you start from here at C, from C 2 cm at 2 cm F, and from F the center O, then another F this side, and C. That is, you draw a straight line first, and then keeping your compass at C, you take 2 cm and mark this point, then F to O, another 2 cm, then 2 cm. So total you have 1, 2, 3, 4, 5 points. Whereas for the mirror you had only 3 points. Now here both the sides. Now we know that this is principal focus, and this is the center of curvature, and this is the optical center. Since this is on the same side of the lens, we mark it as f1, and we know that the center of curvature is twice the focal length, okay, or the radius of curvature is twice the focal length. R is equal to 2f. So instead of C, we will mark this as 2f1. Okay, this is f1 and this is 2f1. Actually it is C, so no need to write C. We'll consider this as 2f1. So if this is f1, this one will be f2, and this C will be 2f2. Okay, and then with the scale you will have to draw one perpendicular to this principal axis. You draw one perpendicular dotted line, and that will be our main surface for the refraction of light. The ray of light will pass through this and it will get refracted from this. Okay, now we know we need to draw the lens. For that we can take 2f2 as the center and O little further from O, or whatever height you want for the lens, whatever size you want, you can keep the point there. Okay, your pointer here and pencil here, and draw the arc. And with the same measure you have to keep it at 2f1 and draw that arc. So your lens is ready. Or you can even draw this lens freehand, because the point of refraction or the line of refraction will be this dotted line. We are going to consider this, not this. So this is our first diagram when the object is kept at infinity. Okay, the object is far away, it's at infinity. Now the rays of light parallel to principal axis, this is center one is your principal axis. So the rays of light parallel to principal axis, after refraction they will meet at f2. Okay, so the image will be formed here. Now where is the image formed? Image is formed at f2. Where was the object? At infinity. Image is formed at f2. Now what is the nature of the image? It is, if the image is formed on the other side, it's called real image. Okay, it is opposite to mirror. In mirror, if the image is formed on the same side, in front of the mirror, it was called real. Whereas in case of a lens, because it is transparent, the rays of light has to pass through the lens. So the real image is formed on the other side of the lens. So it's real, and real images are always inverted, and the size is point sized. And that is what you see in your textbook. Position of the object at infinity. The object is at infinity, far away. Position of the image is at f2. The image is formed at f2. Now what is the size? Highly diminished, point sized. Highly diminished, it's point sized. And the nature of the image, it's real and inverted. Now let us draw the second position from the table. You have an object beyond 2f1. Okay, this is your f1, this 2f1. The object is beyond 2f1. Let the object be AB. Okay, so the first ray will be a ray of light parallel to principal axis. This is your principal axis. Ray of light parallel to principal axis. After refraction, it will pass through F. Okay, this is F. That is F2. So ray of light parallel to principal axis. After refraction, it will pass through the principal focus. So let's draw that. So here it is, a ray of light which is parallel to principal axis. After refraction through a lens, it is passing through the principal focus on the other side. Now the second ray could be a ray, something opposite to this one, parallel to principal axis, after refraction passing through principal focus. Now opposite, a ray of light passing through principal focus. This is the principal focus, passing through principal focus. After refraction, it will travel parallel to principal axis. It will meet here. Or a ray of light which is passing through O, that is optical center. It comes out without any deviation. Whether you draw this one or you draw the other one passing through F parallel to a principal axis, they both will meet at the same point. So to get the image, you require any two rays. So I find this one easier, so I have drawn this. Passing through optical center, it comes out without any deviation, it goes straight, so it will meet here. So the image will be formed here, so you'll have to draw the image here. So this is your image, A bar, B bar. Okay, now let's compare. The position of the object is beyond 2f1, the position of the image between f2 and 2f2. Okay, that's the position of the image. Now what is the size of the image? See this size. Now this is smaller, so diminished. And what is the nature of the image? Because the image is formed on the other side, it is called real. And real images are always inverted, so you can see this is upside down. So the nature is, it is real and inverted. Now let's check that in the textbook. So it's beyond 2f1. The image is formed between f2 and 2f2. It is diminished, real and inverted. See the next position. Now your object AB is kept at 2f1. So you can see a ray of light parallel to principal axis. After refraction, it will pass through f2. And the second one, a ray of light passing through optical center, comes out without any deviation. They both meet here at this point. So if you draw this perpendicular line, that will be your image A bar, B bar, and it is at 2f2. So what is the position of the object at 2f1? What is the position of the image at 2f2? Now what is the size? It's of the same size. The size is same. So size of the image is same. And what is the nature? Because it's formed on the other side of the lens, it is real and inverted. You have the next position when the object is kept between f1 and 2f1. Object AB, ray of light parallel to principal axis. After refraction, it will pass through f. And another one, this passing through optical center, comes out without any deviation. Or you can draw the other one, passing through principal focus. After refraction, it will travel parallel to principal axis. Okay, so whichever you draw, it will meet at this point. So this is B bar, A bar. This is the image. So what is the position of the object between 2f1 and f1? What is the position of the image beyond 2f2? What is the size? See this size of the object. This is the image. It is enlarged. And what is the nature? It's on the other side. So it's called a real image, and real images are always inverted. Now this one is very important when the object is kept at f1. When the object is kept at f1, you can see ray of light parallel to principal axis. After refraction, it will pass through f2 or principal focus, and the other one passing through the optical center, comes out without any deviation. Now they will meet, but not very close to this lens, but it will meet far away, and that will be at infinity. So the image is formed at infinity, and the size will be larger. It will be highly enlarged image because these rays will meet far away. So as you go away from this, the size of the image will keep on increasing. If you look at this figure, see the size. It was here between f2 and 2f2, so size is small. Then now when the image is at f2, it is little bigger. That's almost the same size. Then as you go beyond 2f2, the size keeps on increasing. So in that case, if you see this one, it is going to meet far away. So as the distance increases, the size increases. So only in this case, when the object is kept at f1, then the size of the image will be highly enlarged, and it is real and inverted. Now this next position, let us draw this one. So let's see this position. The object is kept between optical center and F1. This is the object. So first let's draw a ray of light parallel to principal axis. After refraction it will pass through F2. That's this one, a ray of light parallel to principal axis, after reflection passing through F2. Now let's draw another one that is passing through the optical center. But after drawing this, you see that they are not going to meet because they are diverging. They are neither parallel or they are converging, but they are diverging. So they will never meet this side. So what we have to do, we have to extend this backward. So when I extend them backward, they appear to meet here at this point. So here the image will be formed. Now what is the size of the image? Or let's see the position of the object and the image. The position of the object is between optical center and F1 and O. What is the position of the image? It is formed beyond 2F1. Okay, it's beyond 2F1. Now what is the size of the image? See the size of the object. This is enlarged. Now what is the nature? If the image is formed on the other side of the lens, it is called real because the lenses are transparent. So the image should be formed on the other side, that is real. But here it is formed on the same side of the lens. If it is on the same side, it will be virtual, and we know that virtual images are erect. So it's virtual and erect. So you can refer the diagrams that I have drawn, and you can take all this position one by one for the object, that is at infinity, then beyond 2F1, at F1, all these positions. You have got 1, 2, 3, 4, 5, 6 positions. Okay, and draw the ray diagram for all that one by one. Now for concave lenses there are only 2 positions. Convex lenses there are 6 positions, so 6 ray diagrams, and for this only 2. One, when the object is kept at infinity. When the object is kept at infinity, the ray of light parallel to principal axis, after refraction they will diverge. So they will never meet. So you have to draw backward, and whenever you are drawing backward on the same side, it should be with dotted lines because they are not real. They are virtual. So they meet at F1. And the second is between 2F1 and F1. The ray of light parallel to principal axis, after refraction it will diverge, here passing through optical center, so they both appear to meet here. So the image is formed on the same side between optical center and F1. Only 2 positions for the concave lenses. Now your lens can be a freehand figure, or you can keep the compass at 2F2, 2F1 and draw this one, and other side 2F2 and draw this arc and draw this and join them, join the ends. Or this could be freehand. Why? Because we are considering only that perpendicular line, that dotted line, from that surface the rays will refract, not from these curves or the arcs. Okay. So once again I repeat that your homework is you have to draw all the ray diagrams for the 6 positions of the object for not a concave but for convex lens. Okay, you can refer this table for the position of the object. So that's all in this class. Thank you so much and God bless you all.